Welcome to another podcast. This episode, we're going to be taking a look at eigenvalue problems. This is our first sort of exposure to a classical eigenvalue problem here in PDEs. And it's going to lay the foundation for much of the work left in the semester. Specifically, we're going to be taking a look at the separation of variables technique coming up, and solving eigenvalue problems is at the heart of that technique. Let me begin by describing generally what an eigenvalue problem is. In linear algebra, an eigenvalue problem is to recover the value of lambda such that a matrix acting on this vector x behaves like a constant acting on the vector x. In this case, we would have called this the eigenvector, and we would have called this the eigenvalue. So that's what the problem looks like from a linear algebra perspective. However, in differential equations, we have a slightly different take on this problem. In differential equations, the form is some operator acting on y, which is a function, and giving us back a constant multiple of y. So here, L is an operator. It could be an ODE or a PDE or whatever the case may be. It's a differential operator. Y is an unknown function, usually thought of as the solution to our problem. We're going to call it the eigenfunction, though. And lambda then is still called an eigenvalue. So I want to take a look at an example of this. We're going to work through some of the specifics and see if we can't figure out what the eigenvalues and eigenvectors are. So the example I want to work through, we're looking at y double prime plus lambda y equal to 0. And we're going to make this a boundary value problem. So I know values of the solution at the boundaries. In particular, y at minus pi and y at pi are both going to be 0. Now, to express it as an actual eigenvalue problem, what you should probably note is that if I rewrote the equation as minus y double prime, that's equal to lambda y. And if I let L be defined as the operator minus the second derivative, this is the ordinary derivative, then this is basically saying I'm looking at Ly, and I get lambda y. So we are in the situation where we would be talking about an eigenvalue problem. Now, L is the operator here of the equation that we're dealing with, and we're going to talk about some operator theory later in the semester, but the operators we're dealing with have to have certain properties in order for us to get certain types of solutions out of our eigenvalue problems. And if they do, then we have certain characteristics that our eigenfunctions and eigenvalues must satisfy. But we're going to talk more about that later in the semester. For now, we're just going to try to figure out what is the solution to this equation. So we know that if I'm looking at this particular equation, in the case where, let's say, lambda is equal to 0, in this case, we know that y double prime would equal 0, which would imply that y is some sort of linear function. I'll write it as ax plus b. And if I apply the initial conditions, then I know that, the boundary conditions, then I know y at pi is a times pi plus b, and y at negative pi is negative a pi plus b. So this implies that looking at these two, because they're both going to have to be equal to 0. If we add these two, that tells me that 2b is 0 or b is 0. And if we subtract the two, then we have to have 2a pi is 0, which implies that a is 0. Which means that we're basically stuck with the 0 function. Now, the 0 function is called the trivial solution, and when lambda is equal to 0, what we've just shown is that we have only the trivial solution. So an eigenvalue is a value for which you get a non-trivial solution. This means that lambda equal to 0 is not an eigenvalue for this problem. Now, technically we would need to do cases, and the reason that we would need to do cases, if you want to think of it this way, is when I look at this particular equation, we know that the characteristic equation is of the form r squared plus lambda equal to 0, so that r is plus or minus I times the square root of lambda. So if lambda is greater than 0, we end up getting oscillations to occur. If lambda is less than 0, we get no oscillations to occur. So if I'm looking at this and I know my boundaries are both 0, then in the case where I have oscillations, I might get non-trivial solutions because I have the ability that once I leave 0 to come back to it. But if lambda is less than 0, I'm not going to end up with any oscillations here. And so I encourage you to check, but when lambda is less than 0, we're going to get no eigenvalues in this case because the only solution that we're going to get is the trivial solution y of x equal to 0 in those cases. So instead, I want to take a look at the case where we get oscillations and potentially we might find non-trivial solutions, and that's the case where lambda is greater than 0. So if lambda is greater than 0, then we know that our characteristic roots are complex of this form, and so our solution is a constant multiple of a cosine square root lambda x plus b sine square root of lambda x. And applying the boundary conditions, we end up with y at pi is a cosine square root of lambda x, square root of lambda pi plus b sine square root of lambda pi. And using the fact that cosine is an even function, for negative pi it's just the same. But for negative pi and sine, since it's odd, it's going to spit out the negative. And so this is what we'll have in the case where we're looking at y of negative pi. Now both of these are equal to 0. And so once again, if I add them, then that implies that 2a cosine square root of lambda pi is 0. So that means that either a is 0 or cosine of square root lambda pi is 0. Now we're going to take each of these cases one at a time. Let's start with the possibility that cosine of square root of lambda pi is 0. So if the cosine is 0, then we know that the square root of lambda has to be an odd multiple of pi halves, or it has to be an odd multiple of 1/2, because we need to have odd multiples of pi halves in here. So I know that this is equal to some value, I'll say 2n plus 1 over 2, where n ranges from 0 to 1, 2, and so on. In other words, this has to be odd. I need this to be an odd number on top because I need an odd multiple of 1/2 in order for cosine to be 0. Okay, so simple enough. If that's the case, then plugging that value of square root of lambda into the other side, so if I just take the first equation, then this is going to imply that if I plug this in here, so let me show you here. If I plug this value in right here, then I know that term is 0, and I'll be left with b sine of this has to be equal to 0. So I need b sine of the, let's see here, 2n plus 1 halves pi. I need that to be 0. Well, in order for that to be 0, I have to have integer multiples of pi. So I know this guy is going to be plus or minus 1 at odd multiples of pi halves, which means the only way that this can be 0 is if b is 0. So what I've discovered in this first case, where I let cosine be 0, is that I have a function of the form y of x is equal to a times cosine of 2n plus 1 over 2x. I know that is a solution that corresponds to lambda being 2n plus 1 halves, where n goes from 0, 1, and 2. So all of those are possible solutions corresponding to these lambdas in that case. All right. Let me make myself a little bit of room here. The second possibility, so coming back to where we were right here, the second possibility is that a is 0. So if a is 0, then that implies that b sine square root of lambda pi is 0. So looking at this top equation, if a is 0, I've got to have this term be equal to 0. Now, unlike case 1, where I had a restriction on what lambda could be, here there are no restrictions, and so to make this 0, I have to have square root of lambda equal to any integer n, so n could be 1, 2, and so on. I'll pause for a second here to say, why can't n be equal to 0? Well, n can't be equal to 0 since this would imply lambda equal to 0. And we know that lambda equal to 0 is not an eigenvalue. That was one of the cases that we've already considered. So if you look right here, we've already shown that lambda equal to 0 wasn't an eigenvalue. Well, if you now compare what we have, and in this case, if a is 0, then we don't get any cosine functions. We know that our solutions in this case are all sines. So they're sines of this form. So n pi x. No, sorry, just nx. They're the form nx because we're determining our solutions were of this form here. And so we've shown that square root of lambda has to be n in order for this to work. So we get solutions of this form, and these correspond to values of square root of lambda being n. So if you look at this and kind of take a step back at what we've shown so far, we've managed to show that our eigenvalues are of one of the two following forms. They are either, well, the eigenvalues are actually what lambda is, not what the square root is. So lambda is plus or minus, so if I take the square of both sides, I'm going to get n squared. Or lambda is of the form, going back over here, 2n plus 1 halves squared. These are my possible eigenvalues. Now, if I look at sort of what's going on here, specifically for square root of lambda, I can say that square root of lambda is, because it's either n or this thing, if I start listing them out, for example, when n is 0 over here, so over here, when n is 0, I get 1/2. When n is 1, here I get 3/2, but when n is 1 here, I get 1. Then I get 3/2. In other words, if I start listing them out, what you're going to see is we're going to hit every half along the way. So these are what my square root of lambdas are equal to, which a better way to write that is they're of the form n over 2 for n equal to 1, 2, and so on. So by writing this one single form, I've basically described the eigenvalues that occurred in both cases. And that's very important for us to try to do. In particular, what this shows us is that our lambda is going to be n squared over 4, because we're going to have to square both sides. and this is valid for n goes from 1, 2, and so on. Now, the big question here is, what are our eigenfunctions? And I should subscript this because I get a different lambda, I get a different eigenvalue for each choice of n. So these are all our possible eigenvalues. And then the solutions are also, which are the eigenfunctions, they're also going to change. And I'm going to need some more room here. But the solutions are going to be this. When I have the 1, 2, 3, 4, and so on, then I get sine. When I get the odd ones, so 1/2, 3/2, 5/2, 7/2, I get cosine. So the best way to write this is like this. My eigenfunction is cosine over n over 2, because remember it's cosine of square root x, square root is n over 2. But cosine corresponds to the 1/2, 3/2, 5/2, but that's when n is odd. So if n is odd, that's my eigenfunction. If I look at sine, it's also sine of square root lambda, but sine of square root lambda is n halves. But this one is only for 1, which is 2 over 2, 4 over 2, 6 over 2, and so on. So this is only for when n is even. So taken together, what we now have is our set of eigenfunctions, which are the solutions to this equation, for different associated values of lambda. So in other words, if I try to solve the equation y double prime plus lambda y equal to 0, I now know the solution of that equation. When lambda is these specific values, I can get something that's not 0. And the answers that I get are not 0 are these eigenfunctions. And so being able to find this pairing, the eigenvalues with the eigenfunctions, is a very important problem in applied mathematics, specifically in PDEs. And it's something we're going to be doing a lot of this semester. All right, thank you for watching.